And thank you everyone for joining at this earlier time slot. This is probably 5 hours earlier than usual, but probably suits people more in the Asia time zone, which is probably a good thing, really, that we diversify the time slots. But yeah, right. I think we should get going then. It's 12:32 on 12:32 my time on what is a very sunny London morning, London early afternoon, and it is my absolute pleasure to have Haichao from the Algorand Foundation come and talk in what is the part 2 of this 10-part and 1-year part series we are doing with Algorand, the purpose of which is to educate you about blockchain through the lens of Algorand, tell you everything you need to know, and really give you all the tools from whatever background you're from to really deep dive into the blockchain space, and we hope you do it through Algorand. Today is a more technical event. We'll go into what is a consensus algorithm, how Algorand works. It's kind of one of the most essential parts of a blockchain. It's what makes a blockchain kind of special, quite frankly. And we're very much looking forward to that today. A reminder, I've put the slides in for the event 2 weeks ago. All of our events for this series are going to be online. We're doing 10 general education kind of events. And then we're going to go into a fantastic hackathon and then a follow-on accelerator. More details of that we will share. But for now, and sorry, one more thing. I know we have lots of different student leaders, hackers, developers, researchers joining us, not just on this call now, but who will be watching on YouTube thereafter, who couldn't quite make this earlier time slot. So welcome. Thank you all for joining. We hope you have a great time. If you do have any questions, head over to the Discord or feel free to email or message me both kind of publicly and privately. And I'd be absolutely more than happy to kind of help you out, and George and the rest of the team would do too. Awesome. Without further delay, Haichao, thank you so much for joining us today, and over to you to tell us more about Algorand Consensus.
Thank you, Anthony. Thank you for the introduction, and it's a pleasure for me to be here. I believe I've worked with Anthony for a lot of time, but it's actually the first time I've been spoken on the Encode Club event, and today's session is going to be a little bit technical. It's about the consensus algorithm. It's basically the core of the blockchain technology. It's the thing that keeps the whole system works, make sure the safety and the security of the system is ensured. And without this mechanism, without this consensus algorithm, none of the blockchain industry applications, all the tokens will exist. So this is the core of it. And maybe a little bit about me before I start my session. My name is Haichao. I joined Algorand a year ago. I've been working in the blockchain industry for 4 years. I've always been a technical personnel on the team. And my role right now is to be the developer advocate, to engage with you guys, with developers and the students, and try to teach you guys about blockchain and also Algorand. So let's start with today's session. All right. Also, one thing maybe I want to ask you guys is that I want to get a little bit of feedback on the content. So last week we have Eddie talking about the introduction of blockchain, which is as far as I see, it's a non-technical content. But for today, it's going to be a technical one. So after today's session, I would like to get feedbacks on which kind of do you prefer. Do you prefer non-technical ones or technical ones, so that we can arrange more sessions that you like in the future. Okay, starting with today's session, it will have 2 parts. The first part is introduction to the consensus algorithm. It will include a lot of background knowledge of this chapter of academic, and which will take I think around 40 minutes, and then I will spend around 10 minutes on introducing the Algorand consensus, which is going to be a very rough introduction without telling too much details about it. So first part is introduction to the consensus algorithm. I'm sure that you have heard about a lot of consensus algorithms in your work or on TikTok or something like this. And here I listed some of the consensus algorithms that I learned from people. And as you can see, I put this gesture on the consensus algorithm is because none of these are really the consensus algorithms. If you think that one of these is consensus algorithm, then it's a mistake. And today's session will tell you why this is a mistake. And consensus algorithm is actually comes from a subcategory of computer science, which is called distributed system field. And the distributed system is very common in our daily life. For example, on plane, a plane will have multiple computers working together, and they will talk to each other. They will communicate with each other to work as a whole system, to serve as a single goal, which is to keep the plane safe and make sure it's functional. And this kind of system that has multiple functions, multiple computers, is called a distributed system. And they are connected to each other. They are communicating to each other. To simplify the problem here, a distributed system can be shown as a diagram here. So it will have a lot of nodes, and each node here is actually a computer, and each node will be connected to each other, and through the connection, they send and receive internet message to each other, and they process these messages and calculate something, and then talk to each other to perform a computational task. And as a client, as a user, you can send a request to this system, the system that consists of multiple nodes, and all of these nodes will work together to process your request and give you a result as a whole system. Okay, I will get to that question later, about how decentralized Algorand is. So Algorand is actually also based on a system like this. So it is a network that consists of multiple nodes, and they communicate with each other. It's a P2P network. So on the level of network decentralization, it is decentralized, if that's your question. And another concept that I need to introduce here is called state machine. So what is a state machine? This is kind of the very original type of computer that we used in the past. So basically, in this dashed box here, you can consider this as a state machine. It will have a initial state, and upon each input, or you can call it event from outside, this could be from a user, or this could be from another computer. So upon receiving each input or event, the state will be, there will be a state transition between the initial state to the next state. So based on the input, the state machine here will calculate the next state based on the input and also the initial state. And then the state of this state machine is getting to state 1. And after getting another input and event, it will have another state transition and will get into state 2, and so on and so on. Yeah, this is just like the finished state automata. I'm not sure how to pronounce that, but this is the state machine, which is a similar concept, which is a very similar concept to that. And after we have state machine, we will have something called a replicated state machine, which is basically to put a bunch of state machines together into a group of it, and then make sure that every state machine has exactly the same state at the same time. So this is done by setting up the initial state for different node here. And a node, by a node, I mean it's a state machine. So if we have 2 state machines here, then we should set up an initial state, the same initial state for this 2 state machine. And then after there is an outside input or event from user or another node, the state will be transited into the next state. And this should happen at the same time for all the different nodes across in this replicated state machine. So a machine like this, we will just name it as replicated state machine. And this is also one kind of the distributed system that we always use. For example, in the cloud service like Amazon, AWS, or Google Cloud, we are using this kind of replicated state machine to store redundant data to prevent if you only store the data on a single computer, and if something bad happens to that computer, then you could lose your data. So we will have this kind of machine, this kind of a mechanism to store data in different machines, and to make sure that even though one of the machine failed, then we can still have all the data stored in some place safe. So this is a concept of the replicated state machine. I see a question here. Yes, I will get to that later. And the challenges for designing a replicated state machine is actually not that obvious. So it is actually very easy to set up the initial state for a replicated state machine. Even though it has multiple computers, you can always set up the initial state for different computers, because you can just do it at the same time. But after that, what can we? How do we do? Can we make sure that all the state after that can be the same among all these different nodes, different computers? So this is the challenges that we need to solve. And to be more precise, it's very hard to decide the sequence of events, which is also to decide the state at any time, is because that there are three reasons. The first one is that we don't have a globally consistent clock, because if we do have a globally consistent clock, we can just use that clock as a reference. But in the real world, we don't have that thing, because at a different place, although it could be very, very similar, but me at China and you guys at Europe or England, there's very, very tiny time difference between our clocks. And because of this difference, it could cause a random, chaos, a mass of order in the sequence of events, which will eventually cause the errors in the sequence of state. So which will at some point in the future, one of the machine will have a different state than the other ones. So this is the first problem. And then another one is that each node could be fought independently, which means that even though we have you are trying to keep all the computers in this replicated state machine to be functional, but you can't predict that maybe one of the node will fail someday in the future. And when that happens, we still need to make sure that the whole system consists of the rest of the functional nodes. The whole system should still be functional to the user, to the outside. And also the internet connection, the messages you send on the internet that are transferred in the network should be reliable, but not always. So we need to be handling that. What's gonna happen if one of the message is delayed, or if one of the messages just don't get to the receiver. And to solve these kind of challenges, to save all of these challenges for a replicated state machine, the solution is called consensus algorithm. So this is exactly the problems that a consensus algorithm need to solve for a replicated state machine. And it also, this term, consensus algorithm, only applies to a replicated state machine, which is one kind of the distributed system. And a reference here is that some argues that the blockchain is basically a distributed clock that is consistent globally. So because we don't have this kind of clock that is consistent somewhere globally, somewhere in the world, and someone argues that maybe blockchain is supposed to be that kind of is a mission of Algorand to beat Ethereum. We are competitors, I will tell you that, but because we are competitors, we should be making this industry forward together. We have a shared interest. We all want to make sure that the blockchain industry will be a mainstream industry in the future, not like a very just an interesting project. We want it to be something can be the infrastructure for the future of finance. I believe on that mission, Ethereum and Algorand have the shared interest, but we have very many differences, which I will come back to later to talk about later. Yeah. So which leads me comes to the definition of consensus algorithm, which is that to solve all of these problems, which means we need to achieve two properties. The first property is called agreement, or you can also call it consistency, which means that all the non-error nodes. So for example, if one of the nodes in the network failed, then all the non-error nodes should be able to agree on a sequence of events, which also means that they are agreeing on a same state at the same time. And these should be generating the same output to the users at any time. So this is called agreement and consistency. Another property here is called termination and liveness. So not only they should be agreeing on the same result at any time, all the non-error nodes should be able to generate and output a result under a certain time. So you cannot tell me that, okay, we are still, as a bunch of nodes, we are still working on reaching the consensus right now, so we cannot tell you the output. Well, you can tell me that, but you need to give me a certain time. Like how many times do you need to get me the result for me? You cannot tell, you can't just work on the consensus all the time and without getting an output under a certain time. So this is called termination, and you can also call it Leibniz. This is the definition of consensus algorithm. So to achieve these two properties, a lot of scientists, a lot of academic people, professors, very big people like Silvio Micali started to working on designing a kind of consensus algorithm that can achieve these two properties. And some people found that during their research, they found that it is impossible to design a consensus algorithm. And this theory is called FLP Impossibility. And FLP here is actually the last name of these three researchers. So in that paper, they basically say that, to rephrase that, they said in that paper, they proved that in a synchronized network, which I will talk about what is this later, in an asynchronized network where messages may be delayed but not lost, there's no consensus algorithm. So there can't be existing a consensus algorithm that is guaranteed to terminate, which means that we achieve the termination properties in every execution for all starting conditions, if at least one node may fail stop. So this means that basically telling that if you want to design a consensus algorithm to rephrase this FLP impossibility theory, it basically tells you that if you want to design a consensus algorithm, then you can either choose to be a synchronous network. You can only use a synchronous network assumption for your network, for your model, or you cannot have the property of termination. So so this is kind of the problem we have at around 1980s. So when these three people found about this theory, which is mathematically proved, which means they are right. So based on this research, a lot of other people are starting to design consensus algorithms and trying to get around this FLP impossibility. We are finding that building and operating regularly, but much more. Okay, I will take these questions later at the end of this session. So which leads us to a very important assumption that we need to make when we are trying to design a consensus algorithm, which is called network model consumption. So first of all, there are two kinds of networks in the real world. First one is a synchronous network, which means that in this network, any messages signed through the internet, the network message delay can be indefinite, which means that you may never receive a message sent from your friend. This is actually closer to the situation in the real world because the network is not always reliable. Sometimes you just lose power in your house. Sometimes you just didn't pay your internet bill. And so this could happen. And another situation is called a synchronous network, which is the exactly opposite of a synchronous network. This means that every network message delay is lower than a certain amount. So which means that in this kind of network, you are given a certain time frame that inside of this certain time frame, you would definitely receive the message that you should be receiving. And this is the most promising network situation, which is very promising, a very ideal one. And you can only use this kind of synchronized network model in short distance hardware networks, like the example I giving you, like the example of the plane, that all the computers are connected to each other through hardwired, and they have very short distance, so you can consider them to be reliable. So apart from these two network situations, to design a consensus algorithm, the researchers proposed a third kind of network model, which is called a partial asynchronous network model. And this network model basically says that sometimes this network is asynchronous, and sometimes the network is asynchronous. And and by this sometimes they just call it good day or bad day. So on a good day, the network is synchronized, and on a bad day, the network is asynchronous. And by using this kind of partial asynchronous network model, we can get around the FLP impossibility in the future. I just mentioned a bit above. So this is also the very common assumption that most of the consensus algorithms takes to design their consensus algorithm. And this applies to Algorand as well. Algorand is using the partial asynchronous network model as well. So for the questions, I think I will just answer the session related questions first. And after the session, I will answer all the other questions at one time. And after introduced to you what is consensus algorithm and about the network model assumption, I'd like to give you an example of consensus algorithm. So this one is called Paxos consensus algorithm. So this algorithm is still being used in all the cloud services for their replicated state machines, including Google Cloud and Amazon. And the diagram here basically shows how this one works, but I will not get into the details of it because I'm not that familiar with this either. But what I know is that this one is actually using a synchronized network, which makes that it's still be constrained under the FLP impossibility, which means that it only works for the most of time, but not always. So because in a data center, all the computers are connected to each other with hardware, so they can use this kind of synchronous network assumption. But in the real world, if you want to apply this to a blockchain system, which is distributed globally, then this is not going to work. And another challenge we need to be facing when it comes to the blockchain context is called Byzantine fault tolerance. And this problem basically says that it tells this problem by giving a story, which I'm sure that some of you have heard about. So let's say we have different people are trying to attack the city, and if they all coordinate together, they will succeed. But if there are some traitors among them which behave at their own interest and are trying to jeopardize the whole crew, then the attack is going to be failed. So this applies to the blockchain context, because in a blockchain system, all the nodes, all the computers doesn't have a shared interest unless there are some kind of constraint. So let's say if I'm a node in a blockchain on Algorand and I want to double spend my money to make profit for myself, I can just do that without any constraint. So this is the problem we need to solve with a consensus algorithm as well. And this kind of consensus algorithm is called BFT consensus algorithm, the Byzantine fault tolerance consensus algorithm. So to design a BFT consensus algorithm that solve this problem as well, we need to make another assumption. As usual, when we have some problem, we just make an assumption to get around this problem, and then design the system based on this assumption. This is a very common method we take being researcher. So the BFT security assumption, which basically is similar among all the different consensus algorithms. This one suggests that at most there should be 1/3 of the nodes are malicious. So no more than 1/3 of nodes should be malicious, which also means that to rephrase it, at least 2/3 of the nodes should be good nodes, and 1/3 of the nodes can be bad nodes. And this actually applies to a lot of the consensus algorithms, including Algorand here, and others, including PBFT, Tendermint, and Hotstaff, which I will introduce a little bit later. And this also only applies to quorum-based consensus algorithm, which means that this consensus algorithms will be relied on votings from all the different nodes and all the different participants. So in a blockchain system, we don't have this security assumption because there's no constraint to the nodes, no runners to constrain them to do so, which means that we need to design a system to constrain all the node to achieve this security assumption before all these nodes get into the process of the consensus algorithm itself. So this is one of the common mistakes that is being made by a lot of people in this industry. The proof of work, the proof of stake, or proof of anything here is actually node permission system mechanism, is for preventing the nodes getting into the consensus algorithm, and themselves are not the consensus algorithms. So this is a common mistake I mentioned in the first slide. And to get this kind of node permission mechanism, we mostly just use some kind of economic incentives. For example, the proof of work mechanism will ensure that if you want to be a malicious node, then you're going to pay a very, very huge cost to being malicious. You need to spend a lot of money on getting many machines and getting many powers to be a successful attacker. Otherwise, there's no chance for you to do so. And to do that, it will cost a very, very big cost for you, and which will at the end of the day will result in that the cost of you being malicious is actually larger than the benefit that you can receive after you succeed. So we always say that the best way to evaluate the security of a system is not to find how many bugs that this system has. It's really just to evaluate how large the attacking cost is, and to compare that with the attacking benefit. So this also explains that why a lot of the website have a lot of bugs and they don't care about it. So if you are hacking a website from the police station, and your attacking cost is not just a bunch of computers and paying for the power bill, you could also get arrested, and that is very huge attacking cost comparing to what you can get from the attacking benefit. So no one will get benefit from it, so no one will attack it. And the second one here is proof of stake, which is to ask the node to stake to deposit some money, and if they do something bad, then the money will be slashed and they will get hurt. So this is also one way to give them incentives to protect the network. And the third one is proof of authority, basically similar to proof of stake, but this time they put their authority at stake instead of some real money. And to give you an example on the BFT consensus algorithm, PBFT is very, very classical. It's a very classical one. And basically in this diagram, you can see that the first one here is client, the user, and the rest of them are nodes. And the two red nodes here are failed nodes. You can see them somehow broken offline, or they are just trying to be malicious, trying to send the wrong messages or whatsoever. This is the flow of the PBFT consensus algorithm. So the first step is that the user will send a request to the network, and the request will be sent to one of the nodes in the network. And after this node receiving the message, it will propose this message. It's not sending them. Maybe it's not sending the wrong message, so it will only propose a message to the rest of the nodes in the network. And then after receiving this message, each of the node will send the message to the other nodes again, and then they will send it after they receive the message from a different node, and they will just send the message to the rest of the nodes again. So they will do this twice. And this process is actually a voting process, because if you are sending a message to the other nodes, then it means that you are convinced that this message is authentic. You think this message is valid, and you are doing this twice because that we need to reach a threshold in the network among the nodes, so that all the nodes in the network knows that, okay, I know this message is valid, and also I know that you know this message is valid, And on the third level, I also need to know that I know this message is valid. And to achieve that, we need to do two rounds of vote, which means we need to send the message twice. And after that, we will reach the consensus. So what I just described is a very intuitive explanation to this. But in theory, there is a mathematical proof to this kind of process to prove that this process is actually good. It works. No matter how there are two nodes being malicious or failed, this system will still work. But there's one exception in this workflow, which is that what if the first node here, this one here, is a bad node? What if he sends an invalid message to all the network, and then all the other nodes will not be able to receive a valid message because this valid message doesn't exist in the network. After the user sent it to the first node, the node just destroyed it and sent a wrong message to the network. So if this happens, the system will detect that action. And after it detects it, this round of consensus effort is going to be abandoned. And there will be a process called view change, which is basically to change the leader who's proposing the message to the network. And in that way, this one will not be able to propose the message in the next round. The user should be sending the message to the next one. And the next one should be leader for the next round. And then they will go through this consensus process again to trying to reach the consensus. And if it's not still a broken round, then it will be abandoned, and there will be a view change. The leader will be changed, and then it goes through it again. How fast do the votes for consensus happen, and how often? It depending on a lot of parameters, including how many nodes are there, and which is basically constrained by the network bandwidth, and also constrained by the size of the message. So if you are sending a 2 megabytes of message, which is what Bitcoin Cash is doing, 4 megabytes or 2 megabytes, I don't remember, then this message is very large and it's gonna be very, very slow. And after the message, the block is getting into the network, right after that, all the nodes should be doing 2 rounds of voting on that. How many nodes? There's a link that you can get to it. I will send it to you later. Since I'm already, so I'll send this link to you and you can check it out there. Sorry, let me get back to my presentation. So this is the first example of BFD consensus algorithm. And the next one is called Tendermint. So this is actually very similar to PBFT, but the difference is that it has a very different method when processing the view change workflow. So as you can see here, it is a loop that it will always be keeping inside of this loop. So the view change will be processed inside of this loop as well. So it's gonna save a lot of time when it comes to a broken round. And I think Tendermint is 1 order faster than the PBFT in this case. So to summarize on the previous solutions I mentioned and all the ones that I didn't mention, we can just basically categorize the consensus algorithm into 2 types. One of them is POW based, which is a very, very special kind of consensus algorithm because in other kinds of consensus algorithm, as you can see that, there are multiple nodes are voting for the block, for the message together. But in the proof of work proof of work based consensus algorithm, such as Nakamoto consensus used in the Bitcoin, it will only be 1 people voting for the block, which is chosen by the proof of work node permission mechanism. So after all the nodes in the network trying to get through the node permission mechanism, only 1 node will be selected to vote for the block. And after there's no point to reach consensus because there's only 1 node getting into the consensus, which is letting the node to select the block itself, and all the other work are done by the proof of work mechanism. So this is a very special kind of consensus algorithm. Some even argues that this is not a consensus algorithm. This is just a very unique, special kind of consensus. A lot of researchers believe that this should not be discussed in the consensus research. So, which also, in my opinion, also suggests how Nakamoto Satoshi is a great people. And apart from this one, we have PBFT, Tendermint, and Hall stuff, which are all quorum-based consensus algorithm, which means that there will be multiple nodes voting for the valid block, for the valid message at the same time. And after their voting result, they will get the result on which block, which message is valid for this round, and they will reach consensus only after the voting. And to compare these two kind of solutions, one of the drawbacks of proof of work based consensus is that it will have forks. This is fixed by the longest chain protocol, which is that all the nodes will by default to choose even though there could be forks, there will be a network partition. All of the nodes in the network will choose to work on the longest chain at the moment, and they will eventually reach the consensus on a block after 6 or 7 blocks. And the finality, here actually means the finality speed. So how fast can a consensus algorithm achieve consensus? The proof of work is relatively slow because it's a very, very large network. It will have a lot of the nodes in the system, and the block need to be propagated among all the different nodes to get consensus. And it's very fast for quorum-based consensus because there's only little size group of nodes in the network. So it's very fast for them to decide on the consensus. The other difference is on nodes. Proof of work one can be limitless number of nodes. So it can be very decentralized if you put it that way. And PBFT or Tendermint, Hall stuff, this kind of quorum-based can only have a limited number of nodes. In my past experience, it should be no larger than 100 nodes in this kind of network. And after 100, the network is going to be very, very slow, which will eventually make the consensus algorithm non-functional. And the permission perspective, the proof of work blockchain will always be permissionless. Anyone could join the blockchain to be a node. But for this kind of consensus algorithms, the PBFT, Tendermint, Hall stuff based, quorum based, they can only have a permissioned mechanism for it because it will only be able to have a limited number of nodes in the network. And I believe some blockchain can only accept 21 nodes in their network, which I will not mention their name. And another problem here is called partition resilient. This is actually a very interesting problem because proof of work always have forks, which is also network partition, but it will not be recovering from it because all the nodes will just choose the longest chain to work on. But same for all the other quorum-based blockchain, they also cannot be recovering from a network partition. So if someone is DDoS attacking the network to attacking some nodes, then the whole network could be divided into 2 networks, 2 subnetworks, and these 2 networks just work as 2 standalone networks, and they cannot be recovered and merged into one again. So this is one kind of the problem we need to solve as well. And then entering into the Algorand consensus algorithm. First, I'd like to give you a high-level explanation on the Algorand consensus algorithm. It is based on a pure proof-of-stake node permission mechanism. This is only the name of the node permission mechanism. It's not the name of the consensus algorithm. The name of the consensus algorithm is still called Algorand. And this node permission mechanism has a lot of very good features, including you don't have to lock any tokens. just comparing to proof of stake, normal proof of stake, which require you to lock tokens to become a node in the network. We don't ask you to lock any tokens, and also there's no slash mechanism, so no punishment. So you don't have any stress to getting the network to be a node. And but by holding tokens in your hand, in your account, you will have voting powers. So the more tokens you have on your account will mean that you will have more voting powers. And the more tokens you have, which will give you more incentives to protect this network, because the more token you have, then you definitely don't want the network to be broken. And because if it does, then all your tokens will be valueless, will be just thin air. It will be no value for them. So you want to protect the network because you are holding a lot of tokens. So the Algorand X protocol is actually making use of this kind of mechanism, incentive mechanism, to create the BFT security assumption for the Algorand consensus algorithm. And after all the nodes getting through the pure proof of stake, which is a node permission mechanism, they are eligible to become a participant in the consensus algorithm, in the Algorand consensus algorithm. And then they will go through 2 steps. And here I'd like to introduce a very important tool, which is the core of the Algorand consensus algorithm. It's called a VRF, the verified random function. So Professor Silvio actually designed this algorithm because he's very familiar with this verified random function, and he's making very good use of it. So basically, this function allows you to draw a lottery to run a random function on your own machine offline without connecting to any other nodes. You can just run this lottery and to get a random number. And after you're getting this random number, it will also give you a proof to let you convince other people that your number, the number you just got, is actually randomly generalized. It's not some number that you choose by yourself. It is indeed a random number. It will give you a proof of it. And by having this kind of function, the whole Algorand consensus algorithm is enabled based on this function. And all the nodes, after going through the node permission mechanism, you need to go through 2 steps. The first one is that it's called cryptographic sortition. They need to choose a leader among all the nodes in the network. There could be, I forgot how many nodes are there. Maybe I should check out the website. I think if there's 2,000 nodes, then we definitely need to choose a leader among all the 2,000 nodes. And the way we do that is that each user, each node, will run a lottery on their own machine by using the VRF function. And then after they got their lottery, they will know that they will know that if they can be the leader in this round of consensus, and if they are indeed selected, they should be the leader, should be proposing a new block to the network. And one thing I should mention here is that all the node will be running a lottery function, but the possibilities of getting selected to be a leader is actually depending on how many algos does this node hold. So it's not evenly distributed. So the more tokens you have on your account, the more possibility you get to choose to become a leader. So this is also how we apply the pure proof of stake to the consensus algorithm later. And after getting to this step, after we have a leader and propose a new block, we need to do the real consensus process, which is to vote for the new block twice. But we cannot do it among 2,000 nodes because there's just too much of that. As I mentioned, the Algorand is still a quorum-based consensus algorithms. It can only allow no more than 100 nodes at the same time to process a consensus. So what we need to do here is to use the VRF again. So among all the 2,000 nodes, we need to choose a small group of committee to be the consensus participants of this single round, which means that in the real case is that 1,000 tokens will be randomly selected, and they are selected by all the nodes running their own VRF and get their own lottery, and then if they are selected, then you will join a small group of community, and you will be doing consensus with your other colleagues on the proposed new block. And this small community will vote twice to reach consensus. They will vote on the block twice. And to better let you understand this, I'd like to go through this again using some diagrams. The first step here is called block proposal. As I mentioned, all the nodes will run lottery on their own machine, and they will know that if they are selected as a leader in this round. And multiple nodes will be selected because each round will only set up a threshold for the lottery result. Then there could be multiple nodes being selected as a leader, and then each of the leader will go through a round of communication. They will tell each other their proof to prove others that I'm actually holding a lottery, which is generated randomly, and I have the proof for that. And then after they going through this communication, one of them will be selected as the true leader of this round, and this one should be proposing a block. And that is actually based on the lowest block, which means that the hash of the block, no matter what is the lowest value of the hash of the block, then that one will be selected as a leader. So this is kind of like the longest chain protocol. This is called lowest block protocol. After this step, then all the nodes will run the VRF function again, run the lottery again, and because this, for now, they need to select the small group of committee to vote for to reach the consensus on the block, and a group of committee will be selected through this randomly generalized lottery, and then they will communicate to each other by sending messages to each other, very similar to the workflow of PBFT. And then they will just do this twice to vote twice, to be voting twice for the block. After that, they will reach consensus on the proposed block, and then this round of consensus is completed. So this is the workflow of Algorand. As you can see, it's actually very concise because of using the cryptographic tool, the VRF here. Unlike all the other blockchains, which are using a lot of very complicated solutions, the Algorand here is just solving the problem by using VRF, and it's a very simple solution. It's very concise, elegant, and it's mathematically proved. The paper of Algorand is submitted to SOSP, which is a very top conference in the computing system field, and it was accepted on 2015, I think. And then and that conference only accepted two papers. One of them is Algorand, another one is Stellar. So in conclusion, we have three kinds of consensus algorithms in the world right now. One of them is proof of work based. The Ethereum or Bitcoin are using this one, and another one is call room based permissioned blockchain consensus algorithms, including Tendermint and PBFT. And the third one, which is pioneered by Algorand, is called cryptographic based consensus algorithms, because Algorand is basically the first consensus algorithm that is making use of the cryptographic tool to simplify the problem. And the properties here, as you can see, it has all the good features, good properties of the other two kinds of consensus algorithms. It doesn't have fork. It has a very fast finality. All the blocks are finalized in a single block, and the nodes number can be limitless, and it's permissionless. And it also supports partition resilient. Okay, I got a question. I'm not sure PBFT is not partition resilient. So yeah, this is actually a very tricky problem because network partition can be solved by an external tool, because and this external tool can be not cannot be it could not be a part of the consensus algorithms. So if you are trying to use PBFT on a blockchain, you can still solve this problem by using a network recover tool to quickly recover the network after the network partition. So, but in the case of Algorand, we just included that tool inside of the consensus protocol to make this product, this Algorand consensus algorithm, be partition resilient. Okay, I think I'm ready to take questions. So before I finish, there are something I want to mention, which is we have this website right now. You can get on it to help us grow the ecosystem of Algorand and earn some algos. And we have some developer resources on our developer portal, and join our Discord. Thank you very much. I will start to take all the questions starting from the first one. Let me see. Can I explain how decentralized Algorand is? There are different levels of decentralization we're talking about here. Before I answer questions, Anthony, do you want to say something? Should I just start to take all the questions?
No, good. Feel free. I'm happy to read them out if you.
Okay. No, I can just do it. Let me just do it together. You can get some rest. So how decentralized Algorand is? There are different levels of decentralization. So on the network level, it is a P2P network, and it is permissionless. So anyone can join the network to be a node, and there's no permission system to prevent you from joining nodes. So it is decentralized. And on the geographic level, we do have a team in Boston, which is pretty centralized. But I'm working at the Algorand Foundation, which is a very distributed team. I'm in China, and most of my colleagues are in Europe, and some of them are in US, so it's decentralized. And also in terms of the token distribution, there's a page that is token dynamics. There's a page which you can get to learn about the decentralization of the token. I'm sending in the chat box. Okay, the next question. Are these like sorry? Can you tell us more about Silvio Micali and his research? I'm writing my thesis on his work. To be frankly, I haven't talked with Silvio Micali either, because we are working on a different team. I'm working at the foundation, and he's working at the Algorand Inc. And there's not so much opportunity for me to talk with him. But I've learned about something about his story about the Algorand. Basically, he won a Turing Award and then started to thinking about the economics and the game theory field. And then he learned about Bitcoin very early, and he has been constantly thinking about the consensus algorithm. And someday in the cafeteria at MIT, he was our chef scientist, Jing Chen, Professor Jing Chen, which is also his student. They just having this discussion on applying cryptographic tools in the consensus algorithm. And then they found this solution, which is called Algorand. And then they wrote a paper, started a startup, and launched the mainnet. And today, is the mission of Algorand to beat Ethereum? Nope. Diplomatically speaking, nope. We are competitors, but we are working on the same goal here. We are finding that building and operating regulated financial service is cheaper and easier on Algorand. Ethereum is great for DeFi, but much more for regulated finance. Yeah, that's true. That's very true, because the whole Algorand tech stack was designed to be an infrastructure for finance tools and finance products, financial assets. And we started as this with this vision in our mind. And the difference on Ethereum is that Ethereum started as a world computer. The VM, Ethereum virtual machine, a Solidity-based virtual machine, is actually a computational model, whereas the Algorand virtual machine is a verification model. So we only verify the transaction. We do not calculate the transaction, and which makes a lot of things easier, which makes it more safe. Is Algorand consensus quantum safe? No, it's not quantum safe because we are still using the classic RSA-based cryptographic keys, public keys and private keys. But to be quantum safe, we can just choose a different kind of, after there are quantum safe cryptographic tools, we can just choose that kind of tool to make the consensus quantum safe. Does Algorand have an off-chain solution also? We have something under development. We have an offline off-chain smart contract, but that is really to give developers more options on programming languages. It's not for upgrading the performance of the blockchain, because at the moment the Algorand blockchain still has a lot of capacity to process all the transactions. So we are not worried about upgrading the performance of blockchain itself. The ZK Snark based on Optimism or Martic or MATLAB, their purpose is because of the performance of the Ethereum is slow. The transaction finality is very slow. So they are trying to solve that problem, and also the transaction fee. What incentives do I have to node an Algorand, to run an Algorand node? You will protect your tokens. So that is the most primitive incentives for you. If you have a lot of tokens in your wallet, let's say 1 billion tokens, which is 1/10 of all the tokens, then you will want to run a node in the Algorand network to protect your token, the value of your tokens. And so if you don't have that kind of incentive, then you can still run node by joining the network and being a participation node, and but you will not be able to earn extra rewards for that, because we are a pure proof of stake mechanism. We don't let you stake tokens to run node, and in return we don't give extra rewards for the node runners. And all the node runners in the Algorand network now, you can call them volunteers, because they want to protect their tokens. How fast do the votes for consensus happen? And how, I think I answered this one. How many nodes are there right now? I think I answered this one. Do you expect there to be many future iterations of proof of stake moving forward, and where will these improvements come from? I would say that the infrastructure level of blockchain industry is pretty settled. So I don't see any new blockchains in these 2 years popping up and show us a very different design, because I think this is it. This is the end of the consensus algorithm story. We already reached the ceiling of this academic field. There will be no more consensus algorithms, better consensus algorithms popping up in the future, because this is not my guess. This is mathematically proved. There is a limitation on how fast it can be and how secure it can be. How does Algorand theoretically fork? We don't have fork. We theoretically do not have fork. Do node operators receive transaction fees? Nope. All the transaction fees will be burned, which means that these benefits will be benefiting all the token holders. It will not be benefiting the node runners only. It will be benefiting the whole network, the whole algo token holders. Partition resilient. What are the problems Algorand consensus could face? I think as the time goes by, if there's a major upgrade on the network bandwidth, which means that people will be able to send bigger messages to each other using the same amount of time in the network, and by that time, we should be upgrading our protocol to allow a bigger size of block to be propagated in the network, because that is the most efficient way. But without that network bandwidth upgrading, which has not been changed for 2 years since our launch, I would say that this is a problem we will face in around 10 or 20 years, but not now. I mean, until the assumption of okay, series partition dispatch availability, until the assumption of 3F plus 1 PPFD its partition resilient dispatch availability. I'm not sure I get this question. Sorry about that. Why the name Algorand? Because the key of our consensus algorithm is verified random function, and it is an algorithm. So we take algo and rand, put it together, called Algorand. What tooling is missing in the Algorand ecosystem? Good news is we don't miss. There's no missing tools in the Algorand ecosystem now, because we spent the whole 2020 year, the whole year of 2020, on the perfection of all the developer tools and all the documents. And right now we are very confident to tell you that any developers will be able to find the learning materials they need to develop on Algorand, and there will be no missing tools in the Algorand ecosystem. What roles are there for researchers to join Algorand? For the Algorand Foundation team, we do have a research team, but we already have enough members for that. But for the Algorand Inc. team, I would suggest you to visit our algorand.com website on the career page. If you find there are any open positions for researchers, I'd encourage you to try it. And other than that, you can click into the link I'm showing. I'm pointing right now, this GitHub link, the Grow Algorand repository. You will find something called a grant program. You can apply for a grant for research. We have some tokens allocated for research only, and they will only be given to researchers as a grant reward. If we miss any, sorry, can you please explain how VRF works and how is it that a powerful adversary cannot cheat? I cannot explain how VRF works in details because I'm not a cryptographic researcher. The only thing I know is that the VRF will allow you to generate a random number offline independently, and then also give you a proof of the random number to let you convince other people that this number is generated randomly. And this is, we apply this in our consensus algorithm to make sure that all the nodes are selected randomly, although they could be offline, although they're having problems connecting to the network, they can still be joining this process of trying to be a node in the network. And this process, the possibility of being selected as a node runner, as a participant in the consensus algorithms, is depending on how many tokens they are holding. And this is kind of the mechanisms that we are using for adversaries, for preventing adversaries. Where is the technical roadmap for Algorand is available? I would say the blog is the best place to do it, to find it. If you go to the resources, research and innovation, I think. Yeah, all these blogs published by Professor Silvio Micali, you can consider them as the roadmap, the technical roadmap. But to be frankly, we don't have a very formal technical roadmap already, because the mainnet, the Algorand mainnet, is already launched and is very stable. It has been working normally for a year, and there's no problem with it. So we don't have to do any modifications on that. The only things we will need to do is improvements. And our focus is actually the ecosystem, the applications that are building on the Algorand, not the Algorand blockchain itself. What funding opportunities are there available within the Algorand ecosystem? How does the grant system work? So I would suggest you to go to this website. We have different kinds of programs for different developers, depending on if you are a solo developer or a team of developers, or what are you working on. If you are a solo developers who are looking to earn some algos from us, I would suggest you to try the developer ambassador program, which is that if you have an idea on writing a tutorial or creating a solution, an application solution, you can write an article for us. We will give you rewards according to this table here. And also we have some bounty programs. So far we only have 3 opening bounties. And I think one of them is taken by someone else already. So we have these 2 available right now. If you want to work on them, just click in and leave a message. And after I receive the message, I will name you as the bounty taker. And you can just work on that, and then you will earn rewards. And for grant program, we basically offer grant to all the projects who are helping to grow the Algorand ecosystem. The details can be found on this website. And we have hackathons and courses, and Encode Club learning series is actually the only featured one on this list. Okay, next question. How does the grant system work? For now, to be frankly, it's pretty centralized. The Algorand Foundation team decides on who can get the grant rewards. But there's one major task for this year, 2021, is that we are designing a on-chain governance protocol, which I believe can be found. Yeah, so this proposal, a proposal for decentralizing Algorand governance. So we are trying to design a on-chain governance protocols, and after we have that, by the end of this year, we will use that system to let the community to vote for the grant projects. So if you join the on-chain governance program, then you will gain voting powers to vote for how the foundation can spend their grant on different projects, and then you will be able to be a contributor on building this ecosystem with us together. You get your node tokens as an early node, sell them. Oh, sorry. You get your tokens as an early node runner, sell them, then there is no incentive. How does the foundation want to handle that? This is a very early historical questions. I think all the early node runners, they will only receive their vesting tokens if they keep on running a node. And after that, and this process will take 5 years. And after that, the whole all-around the ecosystem should be decentralized enough. And because as for now, we already have 2,000 nodes, and the early backers nodes are only, I think, somewhere between 30 to 50, I think. And all the other nodes will just take on the role and run this network together. What are your favorite blockchain projects in the space, Algorand? And how did you get involved with blockchain? I first learned about Bitcoin's white paper and Ethereum's white paper in 2017 when I was in Japan, and it was very fascinating to learn about this new technology, because that is exactly what I was looking for. I wanted to get a new technology to work in that industry, but not AI, because I've known too much people working on AI and they are really smarter than me. And I think I don't have any, I'm not gifted to compete with them. So I choose to go to something that even more pioneer, which is blockchain. And then I got into this industry by finding a job. What happened with Professor Mikhail's incentive to form a steering committee with long-term staking of algos? Yeah, I think this is the governance protocol here, and this will be designed and tested and implemented by the end of this year. So it should be functional at the latest time, the first quarter next year. But for this year, we are going to do a soft launch for sure. Algorand is deflationary. Then isn't there a point where all algos get used in transaction phase? The transaction fee is dynamically changed. So right now it could be around the 0.01 algos, but after more tokens are burned as transaction fees, the amount of algos will be decreasing, which means that the value of each algo will be appreciated, and then the transaction fees will be lower for sure. I found a lot of problems with Algo Center with NFTs. I'm not sure if Algo Center support NFT. Algo Center is designed by a ecosystem partner, but if you do find any problems, feel free to send me an email. I will forward to them. If you do find a bug, we should give you a bounty or grant to you, because this is very important to us. But if you are trying to add some more features, you are also more than welcome to do it. I think maybe the best way, well, just send me an email. Haichao at Algorand Foundation. What's your favorite project built on Algorand? My vision for Algorand in the future is to be the infrastructure for not just the finance. Finance is very general term. I think one subcategory of finance, which is payment. So stable coins and payment. I think that direction is the future of Algorand. We already have USDT and USDC, and since you are mentioning this, I think USDT and USDC are my favorite project. I think USDC maybe is well, both of them are. I think stablecoin, I like all the stablecoin projects because they have potential to be the next generation of payment vehicles. And if they do so, then the Algorand is going to be a very, very important project. Are there any plans to limit the supply of tokens or rewards, or is the plan to continue the current rate of token supply increases indefinitely? There is a matrix. There is this supply cap for the algos, which is 10 billion. Oh, it's not on this page. Well, there is there is limitations on the supply, which is 10 billion, and the distribution of the tokens like this, so it's going to be gradually distributed among different ecosystem parties, which I don't see a problem, and it's not going to be indefinitely, I think. Yeah, I think that's my answer. Oh, I've reached the bottom. I think I've covered all the questions. So
Yeah.
at the end of it, I want to echo this again. Get on this website if you want to earn some algos, and also if you want to learn about Algorand, developer portal is for you, and also please join our Discord to have more discussions there. Okay, thank you, Anthony.
Awesome. What a fantastic event. That was very in-depth in a fantastic way. And I certainly learned a lot. I didn't know I was expecting to learn too much today, but that was absolutely brilliant. For everyone that joined, thank you so much. Thank you for all the great questions. As I said, this is part 2 of quite a long series. So we have an event in 2 weeks' time about setting up your development environment if you want to start coding with Algorand. We're also going to have a few more non-technical events going in the second half, depending on your feedback. We have the programming for the second half of the event. It's not confirmed as yet, just so we can listen to your feedback and then bring you what you want to kind of receive. But Haichao, in the meantime, thank you so much. Have a nice night. It's quite late your time now. And for everyone else that joined today, see you on Discord. See you on the chats. And yeah, thank you all for joining and have a great rest of the day.
Thank you.
Thanks.